Hello everyone, welcome to the Jan 2026 Edexcel Physics Unit 2 video solution. This is the most recent paper. There has not been any questions, exam sessions after this. So understanding each and every single concept of this paper carefully will definitely ensure a decent grade for your exam. What I've also done is I have compiled all the frequently asked questions and answers of Unit 2, and the download link is given in the description. I can promise you, you will get several questions common in your actual exam from this fact sheet. So let's get started. So I already solved this paper in my class, and what I've noticed was this time around, the MCQs were like very straightforward and easy, except for 1 and 2. So let's start. The graph shows how current I varies with potential difference V for an electrical component. The moment you look at this graph, it should be fairly obvious that it is for a diode. Also remember that when it comes to a diode, you need to know for this specific question, you don't need to know this, but you need to know this in general. This point is called the threshold PD, right? Because it needs minimum amount of this voltage to start conducting. And if you keep on increasing the PD in the reverse direction, at one point the diode breaks down. And this is called the BDPD, as in the breakdown potential difference, hence BDPD. So of course this component is a diode. And at times they do ask you to draw graphs like this. Let's move on to question 2. The phone is connected to a charger. The current in the charger is 5 milliampere. Which of the following gives the charge in coulombs entering the phone in 8 minutes? Okay, so what I also need to mention at this stage is Unit 2 is completely dependent on equations. You need to have a very clear understanding and you need to be able to recall all of the equations at a moment's notice, right? So in the fact sheet, I have also included, along with the fact sheet, I have also included a definition sheet as well as a formula sheet. This will really come in handy and you'll get all of those for free. Make sure to click on those while you place them in your cart. A phone is connected to a charger. The current in the charger is 5 milliampere, right? So this should be very basic. The question is asking you about charge. So Q equals IT. I is 5, but in order for my charge to be in coulombs, current cannot be in milliampere. So you have to convert this to ampere, 10 to the power minus 3. And also the time cannot be in minutes. It has to be in seconds. So 8 times 60. So 8 times 60 is 480. So this is basically 5 times 10 to the power minus 3 times 480. So answer is C. Okay, so this is an easy but interesting question. Let's see. The diagram shows some of the energy levels of a hydrogen atom. So guys, every time you come across energy levels in your head, just recall this equation. Energy of the photon is always equal to or will have to be equal to the difference in energy levels, right? So if you look at the first energy level difference, as in if this electron has to jump up to the first excited state, the incoming photon must have an energy equal to the difference in this energy level. So minus 3.4 minus 13.6. So I've done this so many times, I know the value. It's 10.2. So energy difference in energy levels equals to 10.2, and that's exactly the amount of energy that the photon must bring with it, right? Because energy levels are discrete, only certain energy level transitions are possible, right? So the question says Which of the following could not be the energy of the photon? So guys, the minimum amount of energy to jump to this level, because this is the uh, smallest energy level difference, is 10.2. So anything less than 10.2 is not going to work. So answer is 9.8. Now let's move on to question 4. A light-dependent resistor, LDR, is connected in a circuit as shown. The internal resistance of the battery is negligible. The light intensity incident on the LDR increases. Which row of the table describes what happens to the reading on the voltmeter and the ammeter? So this is an amazing question. Please listen to me very carefully. So look at this circuit diagram. You see the only component in the circuit is the LDR. There is no other component, meaning the entire PD of the battery will drop across this LDR. So there is no other component to get it shared with, right? So the PD will always remain constant because there are no other components. But as light intensity increases, we all know as light intensity increases, the resistance decreases. If resistance decreases, the current should increase. So let's check what should be the answer. So the PD should remain same, the current should increase. Let's see. PD stays the same, current increases. Answer should be B. There was one paper, I cannot recall which year was it. This was a really old paper. They asked you to draw a graph that you obtain using a circuit like this. So this would be the shape of the graph. If it's a VI graph, always remember, since there are no other components, the PD across the LDR will always remain constant. So this should be the shape of the graph. PD remains constant at all times, but the current changes, either increases or decreases. But that question was not with an LDR, that was with a thermistor. But the concept remains the same. Okay, so question 5 says, light from two sources, S1 and S2, is in phase. Fine. The light has wavelength lambda and meets at point P as shown. The path difference for the light is lambda by 4. Which of the following is the phase difference in radians at P? So for questions like this, when they give you the path difference and ask you to find out the phase difference and vice versa, I always suggest my students to follow this approach. Check this out. So you draw a cycle like this, one cycle, and you mark, let's say, the upper section with wavelength. Let's say this is lambda, this is lambda by 2, and this would be lambda by 4. And then you mark the bottom section, and this would be 3 by 4 lambda, 3/4. And then you mark the bottom section, but this time not with wavelength, this time with angles, right? So in one cycle you have 2 pi radian, and in half cycle it's pi radian, and in quarter of a cycle it's pi by 2 radian. And now you just link these two. So a phase difference of lambda by 4 should correspond to a phase difference, sorry, my bad, path difference of lambda by 4 should correspond to a phase difference of pi by 2. There you go. And similarly, if the question had asked you about a path difference of, let's say, lambda by 2, this would correspond to a phase difference of pi, and so on. So this is the trick I always ask my students to apply. So now for question 6, a student investigated stationary waves on a string using the apparatus shown. The vibrating length of the string has a mass of 0.005 and a length of 2.5 meter. Which of the following gives the speed of the transverse wave in the string in meter per second. So, like I said previously, Unit 2 is all about recalling being able to recall the relevant equation. So, the speed of the transverse wave on a stationary wave, speed of the transverse wave that produces the stationary wave on a string is always given by V equals root over T by mu, where mu is the mass per unit length. So root over T would be the same as the load. So 20 divided by mu as in mass per unit length. Mass is 0.005 divided by length would be 2.5. So 2.5 goes up. So root over 20 into 2.5 divided by 0.005. 20 into 2.5 divided by 0.005 root over answer. Answer should be B. Sometimes Pearson will ask you questions just to throw you off, like the most simplest of questions, like question 7. Which of the following graphs represent the relationship between frequency f and wavelength lambda of photons? So photons travel at the speed of light. The speed remains constant. So V equals f lambda. If V is constant, f and lambda are inversely proportional, and for all inversely proportional graphs, it's a rectangular hyperbola. This shape is called rectangular hyperbola, by the way. So answer is D. Okay, so for question 8, the circuit diagram shows a potential difference V applied across the ends of a uniform wire of length L. Which of the following gives the potential difference across length X of the wire? So this is a question of potential divider. We all know in series the PD gets shared according to the ratio of resistance. And guess what? Resistance is proportional to the length. So PD also gets shared according to the ratio of length. So up to X out of the total length X. So the PD will get shared according to this ratio. And what is the total PD? Total PD is V. So my answer is V times X by L. Yep, answer is B. This is the first intellectually challenging question so far. A ray of light is traveling through a material of refractive index 1.75. The ray is incident at the boundary with the material of refractive index 1.4. Fine. Which of the following expressions gives the condition for total internal reflection? Right. So we all know that total internal reflection, angle of incidence in the higher refractive index medium should be greater than the critical angle. And what is the critical angle? Critical angle is also the angle of incidence in the higher refractive index medium for which the angle of refraction is 90 degree. And guess what? This is the very common definition of critical angle, which I've also included in the definition sheet. And the link is given in the description. Now, let's apply the equation for refractive index for two different media, right? So the equation is n1 sine theta 1 equals n2 sine theta 2. So n1 is 1.75 sine theta. Let's call this the critical angle for which angle of refraction is 90 degree. So sine C equals n2 is 1.4 times sine theta 2. This is 90. So sine 90 is basically 1. So sine C equals 1.4 by 1.75. So C equals sine inverse 1.4 by 1.75. Now, for total internal reflection to occur, this theta must be greater than C. So this theta must be greater than this value. C is sine inverse 1.4 by 1.75. So let's check. Theta must be greater than sine inverse 1.4 by 1.75. Answer should be A. So for 10, let's see. The longitudinal wave passed through a material. Compressions and rarefactions are formed. Which row of the table is correct? So for this, I want to show you just a small glimpse of my fact sheet. And I have included this in section A, question 12. So I have rephrased this in more generic terms. When longitudinal waves pass through a material, compressions and rarefactions are formed. How does pressure and displacement vary along the wave? Always remember. So let's see. These are regions of compression. These are regions of rarefaction. R stands for rarefaction. C stands for compression. So always remember, displacement is zero at compression as well as zero at the rarefaction, center of the rarefaction. But particles are close together. They're colliding more often. So the pressure is maximum at compressions and particles spread out, so the pressure is minimum at rarefaction. So do not mix up zero with minimum. Remember this. So let's look at the question and the options. So at rarefactions, pressure is minimum and displacement at the center of compressions is zero. So answer should be E. Just what we just saw here. Center of compressions, displacement is zero, and rarefaction, pressure is minimum. There you go. So in section B, we have there is a current of 1.25 ampere in a wire. Calculate the trip velocity of the conduction electrons in the wire. So every time you come across terms like this, trip velocity, there is only one equation in our entire specification that has trip velocity in it, and that's the transport equation. So the equation is I equals nAvq. So just plug in the values. I is 1.25. N is the number of conduction electrons per meter cube. There is another name for this as well. This is called charge carrier density, and that value is 9.0 times 10 to the power 28 times cross-sectional area is also given, which is 2.7 times 10 to the power minus 7 nAv. This is what you have to find out, and you should know, you should have it memorized. The charge of an electron, that is 1.6 times 10 to the power minus 19. So pause the video, plug in the values. So directly substituting the values in your calculator is also part of your practice. So I want you all to do this with me. So make V the subject of the equation and tell me what value you get and match with mine. So the value is 3.2 times 10 to the power minus 4 meter per second. Let's move on to the next question. For question 12, it says the filament in a lamp is a metal wire. A current in the filament causes heating. Explain how the resistance of the filament changes as the temperature of the filament increases. So I see a lot of people randomly memorizing the points from the bar scheme without intuitively understanding what's going on in scenarios like this. So let me give you a visual aid. So here I have a light bulb, and when I close the switch and complete the circuit, the bulb glows. So I want you to focus on what happens, what goes on inside the filament of the bulb, as in the coiled up wire. So these are the red dots are the lattice ions, and the blue stuff are the electrons. So when current flows, you see now there frequency of collision is low, but when current starts flowing, electrons collide with the lattice ions more frequently, and the vibration, the amplitude of vibration of the lattice ions increases, right? Because of the collisions with the electrons and the lattice ions. So these are your marking points. The amplitude of lattice vibration increases. You can include the term lattice ion vibration. That is also acceptable, no problem. There is an increase in frequency of collisions between electrons with the lattice, as in lattice ions. So the resistance increases. So the question basically asked you what would happen to the resistance. So the resistance increases as temperature increases. Now that you had a visual aid for this question, I hope you'll be able to recall these points more effectively during your exam if this comes. Let's move on to the next question. Question 13 says, a student investigated how the potential difference V across a battery varied with current I in the battery. So I see a lot of students, prejudiced students, just reading between the lines and thinking that a VI graph shouldn't look like this. We all know as PD increases, the current increases, but here it shows something different. So every time you see a graph like this, you have to understand that this is not a basic uh, graph of VI for a resistor or any other electrical component for that matter. This is what's going on inside a battery which has internal resistance. And a lot of times, a question asks you to draw the diagram for this circuit to investigate internal resistance. And this is what the diagram looks like. So this is the circuit that you use for investigating internal resistance. So I want to give you a little bit of insight for questions like this. So what's going on here is the battery has an EMF which gets shared across the load resistor as well as the internal resistance, which is not shown here because this is inside the battery, inside the cell. So the equation that you write for this context is EMF equals V, which is the terminal PD, plus IR. IR is the PD across the internal resistance, right? So let's do some rearrangement. V equals minus Ri plus EMF. The reason I'm writing this equation in this format so that it matches this form. And this is in the form y equals mx plus c. Check this out. So when you have a graph of PD against I, PD against I, the negative of the gradient gives the internal resistance and the y-intercept gives the EMF. So you can clearly see the graph cuts the y-axis over here. So this has to be the EMF 1.5. And now let's find out the gradient of the graph. It's a downward sloping line. So you can take up to this as well. This is my change in y-axis and this is my change in x-axis. So n equals change in y-axis would be 0.5 minus 1.5 divided by, and change in x-axis should be 2 minus 0. So the gradient is minus 0.5 minus 1.5 is minus 1. Minus 1 by 2 should be 0.5. So the gradient is minus 0.5, but the negative of the gradient gives the internal resistance. So R should be just 0.5. One more time, the y-intercept gives the EMF as in 1.5, and the negative of the gradient gives me the internal resistance 0.5. So question 14 says an electron is accelerated from rest through a potential difference of 4.8 kilovolt in a cathode ray tube. Show that the kinetic energy gained by the electron is about 7.7 times 10 to the power minus 16. Right. So they're talking about an electron. Right. So you know the charge of an electron and you know the potential difference. And they're asking you for kinetic energy. So how does the electron gain kinetic energy when it's moving through an electric field? Due to electrical work done. So electrical work done, equation for electrical work done is QV. So the kinetic energy gained is also equal to QV. Q being the charge of the electron, 1.6 times 10 to the power minus 19 times V is 4.8 kilovolt is equal to 4800 volt. Oh, you don't have to write volt here. So one more thing, this is a show that question, and for all show that questions, the rule mandated by Pearson is you have to give your answer to one significant figure higher than the show that value. So since the show that value is in 2SF, you have to give your answer at least in 3SF. So the value that I got is 7.68 times 10 to the power minus 16. 7.68 times 10 to the power minus 16. And there is only one exception for the unit rule. That is for show that questions, the unit is not mandatory, but you can still give it. That would be my suggestion. Next, calculate the de Broglie wavelength. That's how it's pronounced. De Broglie wavelength of the electron. So, every time you come across de Broglie wavelength, you just recall the equation of de Broglie wavelength. Lambda equals h by mv. And all of these equations are very carefully curated and clearly given in the definition sheet, the formula sheet that you'll get with the fact sheet. So lambda equals h by p. So h is the Planck's constant, and I will highly recommend you memorize the constants as well. Right? So the value of h is 6.63 times 10 to the power minus 34. So 6.63 times 10 to the power minus 34 divided by, and I will also recommend you memorize the mass of the electron, which is 9.11 times 10 to the power minus 31 times, we just found out V in the previous part of the question. Oh no, we didn't. Oh, that's why it's a 3-mark question, right? So we have to find out V first. So we have the kinetic energy. We all know the equation for kinetic energy is kinetic energy equals half mv squared. I know the value of kinetic energy. I know the mass of the electron. All you do is just make V the subject of the equation. So the V comes down to, the value of V is 4.11 times 10 to the power 7 meter per second. And this is not your final answer. This is an interim calculation. And this is mandated by Pearson that all interim calculations are done to at least 3SF. And you can only give your final value to 2SF. So you plug in V over here, and the lambda that you get is, now since lambda is my final answer, you can round it off to 2SF. So the value I got in my calculator is 1.8 times 10 to the power minus 11. And for final answers, do not ever forget the unit. Lambda would be in meters. Okay, so now let's move on to question 15. The photograph shows a rear window heater in a car. Each metal strip in the heater has a rectangular cross-section of width 1.64 millimeter and height 0.2 millimeter. Show that the resistance of each metal strip is about 5 ohm. Right. So for questions like these, I always request my students to have a visual aid, draw a diagram. So it clearly says it's a rectangular metal strip, right? So let's draw a rectangular metal strip. So there we have our rectangular metal strip. And when you draw the diagram, a lot of times, even the hardest questions become easier to relate. So the width is 1.64. This is 1.64 millimeter. This is given. And the height, this is 0.2 millimeter. And length is also given, 0.95 meter. Be wary of the units, 0.95 meter, right? So like I said, unit 2 is all about being able to recall the relevant equation. And I have already provided the equation list as in the formula sheet along with the fact sheet. The download link is given in the description. So what is the equation that you recall here? So when you have dimensions like this, always remember the equation that you have to recall is resistance equals rho L by A, right? So I do have the resistivity, I have the length, and for area, you just need to multiply this height with the width. This is the cross-sectional area. And like I said previously, always be wary of the units. These are in millimeters. And when you plug in the values, rho is 1.7 times 10 to the power minus 6. Rho L is 0.95 divided by area would be 0.2 millimeter to meter is times 10 to the power minus 3 times the width is 1.64. Again, millimeter to meter is times 10 to the power minus 3. So when you plug in the values, the resistance comes down to, so the value that I got was 4.92. And since it's a show that question, always remember the Pearson mandated rule is the answer has to be at least one SF higher than the show that value. So the show that value is 5, it has to be at least 2 SF, as in 4.9. 4.9 is good enough. So just to be on the safe side, I write down 4.92 ohm. Done. Let's move on to the next part. The heater has 11 identical metal strips connected in parallel as shown. Determine the total resistance of the metal strip. So guys, the keyword that you need to focus on here is identical. Identical is the keyword. So I have a small trick for you, and that is when resistors are connected in identical resistors, I mean when identical resistors are connected in parallel, the total resistance is an individual resistance divided by the number of resistors. So our total would be an individual resistance that we just found out in the previous part of the question. It's 4.92, an individual resistance divided by number of resistors. There is 11, which gives you 0.45 ohm. Let's move on. The potential difference across the heater is 12 volt and the internal resistance is negligible. Determine the current entering the heater. So You see, this question came in part 3, which means it is related to the previous part of the question, as in part 2. So all of these metal strips combined have a total resistance of 0.45. I have the total resistance. I have the total PD. So the total current should be found out using V equals IR. I have V12, I have R 0.45. All you do is just make I the subject of the equation. V is 12. The question is asking for I, and R we just found out 0.45. Therefore, I equals 26.7 ampere. As always, never ever forget the units. Part B says an alternative design is to connect the metal strips in series. Okay, explain why this would not result in the same power being dissipated by the heating circuit. You do not need to include any calculations in your answer. I get it. We don't have to include any calculations, but you do have to recall the equation that you'll have to construct your answer with. So what happens is when you connect resistors in parallel, the total resistance decreases because do you remember we were finding out the total resistance of the 11 metal strips in parallel, so we divided by, right? And conversely, if you connect them in series, you multiply with 11, right? So the total resistance increases, but the total PD remains the same because it's from the battery, it remains the same. So when you recall the equation, power equals V squared by R. The V remains same, but this time when you connect them in series, the total resistance increases, so the power dissipation decreases. So it's a 2-mark question. 1 mark should be for the total resistance is greater now, so the power dissipation would be smaller. So for question 16, it says, a student connects the circuit shown in the diagram. Determine the reading on the voltmeter. So guys, this is a very classic potential divider concept. So what happens is when you connect resistors in series, the total PD, as in the EMF, gets shared according to the ratio of the resistance, right? So the question asks you to find out the PD across the 6.8 kilo ohm. And the other thing you need to remember is the units get cancelled out, so there is no need for conversion. So V equals the resistance corresponding to V is 6.8 divided by total resistance 6.8 plus 4.7. In this ratio, the PD will be shared and the total PD is 3. So the value is 1.77 volt. I hear a lot of students asking me that how many SF should I give my answer to? So when it comes to unit 1 and 2, it's very straightforward. You can give your answer rounded off to 2SF. But there are sometimes exceptions with shorter questions that I've already discussed. The other thing is, my suggestion would be in your calculation, keep your answer in 3SF and in the answer section, round it off to 2SF. So if you round this off, that would be 1.8 volt. Next question says, determine the power dissipated by, look at this, the whole circuit. So if you have to find out the power dissipated by the whole circuit, you need the resistance of the whole circuit, right? So I have PD, I have the total resistance. The equation that links PD with resistance and power is P equals V squared by R. So V was 3 squared divided by R, as in the total resistance would be 6,800 plus 4,700. This time you do have to convert. That is 11,500. So 3 square divided by answer, which gives you 7.8 times 10 to the power minus 4. So, like I just suggested, over here, you write down the answer as in the calculated part in 3SF, 7, and you have to be wary of the rounding off technique. So it's 7.826, that makes it 7.83 times 10 to the power minus 4. What? Do not ever forget the unit. And in the answer section, you write just 7.8 times 10 to the power minus 4. What? There you go. Okay, so the next question, as in part C, says the student connects the battery to an emitter and a motor. There is a current of 2.5 ampere in the motor. Calculate the energy transfer to the motor in 1.5 minutes. So E equals VIT. That's the equation you have to recall. And if you're connecting the same battery, so the V of the battery is 3, I is 2.5, and T, of course, from 1.5 minutes, you have to convert it to seconds into 60. So the value that you get is, like I said, in the calculation part section, write in 3SF, the value is 675. Since it's energy, unit would be joule, and you can always round off your values to 2SF unless it's a shorter question or the question says otherwise, and you round it off to 2SF, the value becomes 680 joule. Question 17 says, a student directed light from a laser onto a diffraction grating. The student saw a series of maxima on the screen. The diagram shows position of the central maximum at O and the first order maximum at X. Fine. Okay, so from this question, this is what you have to focus on. Since you are measuring the distance up to the first order maximum, so in the equation of diffraction grating, the value of n should be 1. Calculate the number of lines per millimeter on the diffraction grating. Right. So every time you come across a question of diffraction grating, always remember the equation at play is n lambda equals d sine theta. So let's first find out theta. Just apply trigonometric function of tan. So tan theta equals opposite 0.78 divided by adjacent 4. So theta equals 0.78 divided by 4, shift tan, answer. It's 11 degree, and like I previously said, since you are measuring the distance from the central maximum to the first order maximum, the value of n is 1. So basically 1 times lambda is 635. Definitely you have to convert nanometer to meter, and the way you do it is by multiplying with 10 to the power minus 9 equals d sine, we just found the angle, 11. So make d the subject of the equation. 635 times 10 to the power minus 9 divided by sine 11 gives you 3.33 times 10 to the power minus 6. 3.33 times 10 to the power minus 6. Guess what? It's in meter. But the question says to find out the number of lines per millimeter, right? And again, when it comes to unit 2, it's all about being able to recall the relevant equation. So the equation that links d with lines per millimeter is d equals 1 by lines per millimeter. But you know what? If you have to apply this equation, D cannot be in meter. You have to convert D to millimeter first. So this D, meter to millimeter, is times 1000, which gives you 3.33 times 10 to the power minus 3 millimeter. Now place this D over here. So lines per millimeter would be 1 by this value. 1 by answer, which gives you 300. There you go. This is your answer. Questions like this, previously, you could get away with just talking about either path difference or phase difference. But now, in the most recent papers, they have mandated you talk about both. You need to address both the path difference and phase difference in questions like this. So, when do you have a maximum, right? When constructive interference takes place. And constructive interference takes place when the waves are in phase or when the path difference is a whole number of wavelengths. So you have to write all of this for this question. So this question says, in 1886, Heinrich Hertz directed radio waves towards a metal plate. The standing wave was with 5 antinodes. Was produced as shown. Explain how antinodes were formed. See, this is a slight variation of the question. How are standing waves formed? This is very similar to that question, but there is a slight twist. You need to focus on the antinodes bit, right? So the transmitted wave and the reflected wave superpose. This gets you 2 marks. And now you need to focus on how antinodes are formed. So these are the positions of antinodes, and antinodes are formed when the waves are in phase. Or this time, this is optional. Antinodes are formed when the path difference is a whole number of wavelengths. So one last time, the incident wave and the reflected wave superpose, and antinodes are formed when the waves are in phase, or antinodes are formed when the waves undergo constructive superposition. Let's move on. Determine a value for the speed of the radio waves in this experiment. Frequency of radio waves is given 157 megahertz. So of course, when you put the values in the equation, you have to convert megahertz to hertz. But let's look at this. So the whole section or segment is 4.75 meters. So let's count how many wavelengths are here. So this is one wavelength. Follow my cursor. This is 2 wavelength, and this is 2.5. So 2.5 lambda equals 4.75. Therefore, lambda should be 4.75 divided by 2.5, which gives you 1.9. So now that I have lambda, you just plug into the equation V equals F lambda. F is 157 times mega means 10 to the power 6 times we just found out that is 1.9, and the value that you get is times 157 times 10 to the power 6. It's 1, 2, 3, 4, 5, 6, 7, 8. 2.98 times 10 to the power 8 meter per second. And even though this is not a show that question, you can say with certainty that this is the right answer, because when you're dealing with radio waves, you have to understand these are electromagnetic waves, and all electromagnetic waves have the same speed of around 3 times 10 to the power 8. So 2.98 is very close to 3 times 10 to the power 8. So next part of the question says, a teacher demonstrated the properties of radio waves. He used an aerial to detect the radio waves. Initially, the aerial was vertical and a maximum intensity of radio waves was detected. The teacher rotated the aerial by 90 degrees, so it was horizontal. He observed that when the aerial was horizontal, radio waves were not detected. Explain this observation. So this is a little bit layered question. When the detector is rotated, the intensity decreases. So when you hear terms like this, it should automatically trigger the part in your brain that contains information about polarization. Right? So do you remember when the filter is rotated 90-degree, intensity drops to minimum, but this only applies to polarized wave. So that means oscillations are in one plane or one direction. This means radio waves must be polarized because only when it comes to polarized waves, the intensity varies between maximum and minimum after every 90-degree rotation. Okay, so for this question, question 19, it says ultrasound can be used to detect cracks in the wing of an airplane as shown. A transducer that emits and receives ultrasound is used to scan the wing. Explain how ultrasound can be used to determine the depth of a crack. Let me give you another insight. Actually, let me show you another question that has the exact same marking points as this one. So the reason I'm showing you this is the context might be different. In your session, you might not get a question using what is it called, a crack in a wing. It can be a completely different context. But the concept, underlying concept, when it comes to ultrasound and pulse and echo remains the same. So this question is from Jan 20, question 13. It says a pulse echo technique using ultrasound can be used to produce images of an unborn baby as shown. Explain how the ultrasound scan of the unborn baby is produced. See, it's a 6 mark question, and the question we were dealing with is also a 6 mark question. And guess what? The marking points are the same. So what I have done is I have compiled all of these into the fact sheet. Okay, you'll get all the common questions in the fact sheet. So make sure you have it memorized before you sit for your exam. And these are marking points. So these are the marking points. Ultrasound is always sent in pulses, and there is a whole topic of discussion regarding why is ultrasound sent in pulses. So we'll come to that later. So the pulses of ultrasound are reflected from the crack, and sometimes you have to mention why does it get reflected from the crack? Because there is a difference in density. So in this paper, this marking scheme, they did not specify why does the pulse get reflected from the crack. But I have seen in several other years, you have to specify, and this is of course included in the fact sheet. Time taken between pulses being sent and received is measured. This part is very, very important. Speed of ultrasound is known. So using the time and the speed, you calculate the distance. So the whole idea of this specific concept is to determine the distance. And you would be wondering, what's with the very last point, using half time or half distance? This is basically when you deal with pulse echo, it's phi equals 2d by t, right? So when you are dealing with the distance, d equals v times t divided by 2. So this is what they meant by half time. Question 20 says, a device called a refractometer can be used to determine the concentration of a solution of glycerol. The graph shows the refractive index for different concentrations of glycerol. So I have a small suggestion for all of you. When you come across questions like this, like unseen contexts, do not be alarmed. The question will have very clear instructions for what you have to do, most of the times. Let's see. In a refractometer, a ray of light is shown through a sample of glycerol and refracts at the surface of a glass block as shown. All right. The refractive index of glass block is 1.75. determine the speed of light in the glass block. So, how do you determine the speed of light in the glass block? So you see, the question says refractive index, mentions refractive index, gives the value, and talks about speed. So you have to recall the equation that links speed with refractive index, and that equation is n equals c by v, where c is the speed of light in air or vacuum, and v is the speed of light in the medium, as in the glass block. So you make v the subject of the equation. So v equals c by, and c is 3 times 10 to the power 8 divided by n is 1.75, which gives you a value of 1.71 times 10 to the power 8 meter per second. And since the beginning of this section, I've been saying that in the calculation segment, write down the answer in 3SF, but in the answer section, round it off to 2SF. So the rounded off value should be 1.7 times 10 to the power 8 meter per second. Next, the table shows the concentration of different samples of glycerol. Deduce which sample is being tested in the refractometer. Right. So this is what you have to deal with. Okay. So most of the times they deliberately give the angles with the surface. That's none of our concern. Always remember, we always find the angles with the normal. So this is my angle in glycerol, and this would be the angle in glass. So this value should be 90 minus 55.1, which gives you 34.9. This is 34.9, and this is 90 minus 64, which gives you 26 degree, right? So back in your IGCSEs, for refractive index with angles, you use the equation n equals sin I by sin R, right? Gone are those days. We don't use that anymore. What we use instead, in the new spec at least, is n1 sin theta 1 equals n2 sin theta 2. So n1 and n2 being the refractive indices in the two media. So in glycerol, uh, what did the question ask me? The question asked me which sample is being tested in the refractometer, right? So we need to find out the refractive index of glycerol. Okay, so n glycerol sin theta in glycerol is 34.9 equals to refractive index of glass. It's given 1.75 times sin theta in glass is 26. So what you do is you find refractive index of glycerol. So the value I got is 1.34. 1.34. Always remember, refractive index doesn't have a unit. Now you go up and check in the graph that 1.34 corresponds to which concentration. So I do have 1.34, the exact value. You go to the right and you see this, right? So this is 2, this is 4, this has to be 3. This is 3, 3.2468. So this is 3.2, and between 3.2 and 3 is 3.1. So 3.1% concentration. Now you go in the table and check 3.1 is closest to 3.2, and it's a deduced question. Always remember, when it comes to deduced questions, there has to be a numerical comparison. So 3.1 is approximately equal to 3.2. Oh, do give percent as well. Therefore, it has to be sample 2. So question B says light rays can be directed through the sample of glycerol at different angles of incidence. One ray of light is shown. Explain why it is not possible for any light from the glycerol to reach the region between X and Y. So when you keep on increasing the angle of incidence, guess what? After this, you cannot increase the angle of incidence anymore, right? So this is the maximum angle of incidence, which corresponds to the maximum angle of refraction. And this is your answer. The ray shows maximum angle of incidence. So this is the maximum angle of refraction for glycerol sample. I know the question was presented in a very complicated manner, but this is a very straightforward answer. Now, this is the last question. A camera detects light using a charged couple device. It's called a CCD. One CCD has an array of metal pixels as shown. The pixels release electrons when exposed to ultraviolet light. The pixels are exposed to UV light of wavelength 380 nanometer. So that the energy of this light, of a photon of this light is about, the value is given, right? So, as always, for any calculation or shortcut question, you just need to recall the relevant equation when it comes to unit 2. So the equation that links wavelength with energy is E equals hc by lambda. So I'll definitely request you to have these constants memorized. The value of Planck's constant is 6.63 times 10 to the power minus 34 times c is the speed of light, 3 times 10 to the power 8 divided by lambda is 380 nanometer, has to be converted to meter, times 10 to the power minus 9, which gives you, so the value that we get is 5.23 times 10 to the power minus 19. 5.23 times 10 to the power minus 19 joule. And as for all shortcut questions, as I've already mentioned previously, always remember answer has to be given to 1 SF higher than the shortcut value. So the shortcut value is in 2 SF, answer has to be given to at least 3 SF. That's a must. Okay, so the next part is really important. The manufacturer states that about 80% of these photons incident on a pixel will cause the emission of an electron. Right. Deduce whether the manufacturer's statement is correct. And they have given you some information. Right. So when you look at the pixels, what shape did they look like to you? To me, it looked like circles. So the pixel's diameter is given. The very first thing, the very first step, and this is what I teach my students, the modular approach. So there will come questions when you cannot relate to it intuitively, or you cannot see through the question. So in questions like those, my suggestion is always just get started with whatever information you have available. For example, I have intensity and diameter. Let's first, you know what, let's not even talk about intensity. Let's just deal with diameter. Every time you see diameter in questions like this, you have to find out the area. So area equals pi d squared by 4. Okay, so this is the equation that I use to directly find out the area. So the area that I get is pi into d would be 1.2 times 10 to the power minus 5 pi d squared by 4. So the value is 1.13. 1.13 times 10 to the power minus 10 meters square. Then using intensity, recall the equation. What is the equation that links intensity with area? It's power in the form of light equals intensity into area. Actually, the equation is intensity equals to power by area. So I'm just making power the subject of the equation. So power equals intensity times area. So I have the intensity 1.1 micro has to be converted times 10 to the power minus 6 times 1.13 times 10 to the power minus 10. 6. So the value is 1.24 times 10 to the power minus 16 watt. All right. Now I'll give you an equation that you might have seen for the very first time. You might have never seen before, and you'll be seeing for the very first time, very likely. And that equation is power equals to energy into frequency. Now you might be wondering, wait a second, what is this? This is basically power equals energy by time. And if I write time a bit separately, energy into 1 by T, and 1 by T is F, right? So F would be the number of photons arriving per second. So F, I can replace F with the number of photons arriving per second. And since it's per second, you can also call it frequency. So therefore, N, number of photons arriving, is power divided by energy. And guess what? This is in part 2. And we had already found out the energy of each photon in the previous part. So N would be, number of photons would be power by energy. Power is 1.24 times 10 to the power minus 16 divided by this energy that we just found out previously. It's 5.23 times 10 to the power minus 19. 5.23 times 10 to the power minus 19. And this gives me 1.24 times 10 to the power minus 16 divided by 5.23 times 10 to the power minus 19. This is 237. So I have 237 photons arriving every second. But out of these 237 photons, only 195 electrons are being emitted. So you need to check what percentage of photons causes photolytic emission. So 195 divided by 237 into 100%. So 195 divided by 237 times 100 gives you 82%. 82%. And the claim was about 80%. It says about. So 82% is approximately equal to 80%. So the claim is correct. And I'm guessing this was a deduced question. Yep. Always remember, when it comes to deduced questions, always give a numerical comparison like this. So this part of the question is one of the hardest questions of the entire paper. I would say a bit harder than the last one that we just did. Okay, so let's see. The threshold frequency of the metal in the pixel is equal to the frequency of green light. All right. So threshold frequency is equal to frequency of just green light. Okay. The pixels were exposed to white light the same intensity as the UV light. The UV light source was removed. Explain how this changed the percentage of photons that release the electrons. Right. So I don't think you understood anything by reading the parts of the question. So let me just directly take you to a visual aid. Let's say this section is for UV, and let's say this section UV light was replaced with white light, but exposed to the same intensity, right? So if you are watching this video, I'm guessing you have covered most of your lectures of Unit 2. So every time you come across intensity, you link it with number of photons. So if they are exposed to the same level of intensity, that means the same number of photons are arriving every second, right? So this is for UV and this is for white light, right? So let me change the color a little bit. Let's use black for colors. So let's say I'll pick seven photons. 1, 2, 3, 4, 5, 6, 7. Guess what? All of these photons have a frequency greater than frequency of green light because that's the threshold frequency. So it means all of these photons, when it comes to UV, can cause photoelectric emission or release electrons, more appropriate term. So all of this will cause the emission of electrons, right? Now, what do you know about white light? It consists of 7 different colors. So let me draw these 7. Let me bring in these 7 photons. But this time, this is not for UV. This is for white. And we all know white has a range of wavelengths, right? Starting from violet, indigo, blue, green, yellow, orange, and red. But the question had specified clearly that the work function, my bad, the threshold frequency was equal to the frequency of green light, meaning only green light and onward or higher frequencies can cause photoelectric emission, right? So these parts of the spectrum, visible light spectrum, can cause the photoelectric emission. So even though these parts are arriving, but they will not be able to cause any emission. Only these parts will cause the emission of electrons, right? So the number of photoelectrons would increase or decrease. You think yourself. This time, all of the UV photons were causing emission, but this time only a certain fraction of the wavelengths are causing photoelectric emission or the emission of electrons. So the question says, percentage of photons released would definitely decrease. Now let's look at the marking points. So there are a range of frequencies or wavelengths in white light that we just saw from here, range of frequencies and wavelengths. And I will also recommend you to memorize the range of wavelengths. Violet corresponds to 400 nanometer and red corresponds to 700 nanometer and green is around 530 nanometer. If you have these reference values memorized, it becomes easier. And anything less than 400, somewhere over here, let's say 300, would definitely fall into the UV region, right? So anyway, so only some frequencies will be higher than the threshold frequency, like here. Only some will be higher than the threshold frequency. Only some photons will have enough energy to release and electron. Only these ones will cause the emission of electron, but these ones won't. And finally, only smaller percentage of photons would release the electrons. Here, all of these photons were releasing the electrons. For white light, a smaller percentage of photons would cause the emission of electrons. Thanks for watching. And if you haven't already subscribed to my channel, please consider doing that. And good luck with your exams. Take care.